For decades, we've been stuck in the sky. Flying from New York to London still takes 8 grueling hours of cramped seats, dry air, and turbulence. Innovation and speed has stalled until now. Imagine boarding a pod, sinking beneath the waves, and launching at 760 miles per hour. A transparent vacuum tube where you can sip your coffee and watch the deep ocean blur past, arriving in London in under an hour. This is the Underwater Hyperloop. With a price tag of $900 billion, is this Elon Musk's ultimate vision for the future, or just an impossible pipe dream? And practically speaking, how on earth would we even build it? Current long-haul flights take agonizing hours, but inside this advanced aerodynamic testing facility, engineers are simulating a future where sleek titanium pods eliminate air resistance, cutting intercontinental travel down to mere minutes. To achieve the vision of a transparent underwater tube, industrial foundries work around the clock forging aluminum oxynitride, a specialized advanced ceramic that is completely transparent but significantly stronger than bulletproof glass. Once cast, these massive transparent segments are transferred to automated polishing bays where diamond-tipped robotic arms ensure a flawless, microscopic finish, allowing passengers to view the deep ocean without compromising structural integrity. To achieve speeds of 1,200 kilometers per hour, the system relies on magnetic levitation. Automated winding facilities produce thousands of dense copper electromagnetic coils, engineered to eliminate mechanical friction entirely. These electromagnetic coils are precisely integrated into titanium track modules on massive assembly lines. This continuous production ensures the track can seamlessly levitate the passenger pods across thousands of miles of ocean. Creating a near-vacuum environment inside the tube is critical to eliminating air resistance. Massive multi-stage industrial vacuum pumps are manufactured continuously, designed to operate relentlessly to maintain zero pressure inside the tunnel. While the tube must be transparent, it requires a rigid backbone. Aerospace-grade titanium is stamped by giant hydraulic presses to form the outer protective shell, designed to withstand crushing hydrostatic deep-sea pressures. Joining advanced ceramics to aerospace titanium requires flawless precision. Automated friction stir welders fuse the framework together without melting the materials, ensuring a pressure-resistant seal capable of surviving the harsh ocean depths. The tube cannot sit on the ocean floor. It must float suspended in the water column. Massive buoyancy pontoons are continuously cast from ultra-high-performance marine concrete to keep the Hyperloop perfectly level. To anchor the floating tube to the seabed, advanced tether cables are woven from a blend of high-tensile steel and carbon nanotubes. These automated braiding machines produce tethers capable of holding millions of tons. Securing the Hyperloop against deep ocean currents requires unimaginable weight. Massive steel anchor blocks are continuously forged in heavy foundries, ready to be dropped into the abyssal plain to secure the tethers. The ocean is never still. To prevent the tube from snapping, hydraulic tensioning systems are assembled and attached to the tethers, automatically adjusting the cable length to absorb the shock of underwater currents. Crossing the mid-Atlantic ridge requires navigating active tectonic plates. Specialized factories vulcanize aerospace titanium with heavy industrial synthetic rubber, creating massive flexible joints that allow the tube to bend during subsea earthquakes. Before deployment, every flexible joint is subjected to brutal mechanical stress tests. Colossal hydraulic rigs pull and twist the structures endlessly, simulating the violent tectonic shifts of the ocean floor to guarantee survival. To survive the pressure paradox, crushing ocean depths on the outside and a complete vacuum on the inside, each tube segment is rigorously evaluated inside massive hyperbaric chambers that simulate extreme deep-sea environments. To prevent barnacles and algae from clouding the transparent tube, automated spray booths apply advanced anti-biofouling coatings. This continuous protective layer ensures the Hyperloop remains structurally sound and perfectly clear for decades. Individual components are shipped to colossal coastal shipyards where they are continuously assembled into massive, 500-meter-long megasections. This high-efficiency prefabrication reduces the hazardous and complex assembly work required out in the open ocean. Before these massive sections leave the shipyard, heavy titanium bulkhead doors are installed at both ends. These automated seals keep the segments perfectly watertight and buoyant while they are towed across the ocean. Once sealed, these gargantuan segments are lifted by colossal gantry cranes and placed directly into the ocean. Specialized tugboats and transport fleets then systematically tow the buoyant sections out toward the installation coordinates. A synchronized fleet of high-powered ocean tugs slowly transports the prefabricated sections out to the mid-Atlantic. This continuous, highly orchestrated logistical ballet brings the pieces of the puzzle directly over the underwater installation site. Directly above the route, specialized construction vessels begin the anchoring process. Massive steel blocks are continuously dropped and lowered miles down to the abyssal plain, laying the heavy foundation for the floating tunnel. In the crushing depths of the ocean floor, fleets of automated, remotely operated vehicles work continuously. Their highly precise robotic arms secure the tether cables to the anchors, preparing the suspension system. Once in position, automated ballast tanks on the floating tube sections are flooded. The gargantuan structures sink in a highly controlled, perfectly level descent, stopping at the exact suspended depth of 50 meters. Connecting the sections underwater requires flawless execution. Specialized subsea welding drones clamp onto the joints, working continuously to fuse the massive titanium rings together, creating a perfectly airtight and structurally sound seal. With the sections sealed, massive industrial manifolds engage. High-powered vacuum pumps run continuously for weeks, sucking millions of cubic feet of air out of the tunnel to achieve the near vacuum required for zero-resistance travel. Safety in a vacuum is paramount. Factories continuously assemble specialized, highly buoyant escape pods. In the event of a catastrophic breach, these pods are designed to automatically detach and float passengers to the surface. These escape pods are integrated into massive titanium airlocks installed along the route. Technicians rigorously test the explosive bolts and pneumatic seals, ensuring the system can rapidly eject passengers into the safety of the ocean. The passenger pods themselves are masterpieces of engineering. Aerospace facilities continuously assemble these sleek, carbon fiber chassis, designed to be incredibly lightweight, yet strong enough to maintain a pressurized cabin inside the vacuum tube. To achieve frictionless flight, the pods are fitted with heavy electromagnetic skids. Technicians and robotic arms install these crucial levitation components with extreme precision, ensuring they will align perfectly with the tube's Maglev track. Inside the factory outfitting bays, the pods are equipped with advanced life support systems and impact-resistant seating. The interior is designed for maximum comfort, masking the terrifying reality of flying at Mach 1 underwater. While passenger travel makes headlines, the real economic driver is high-priority cargo. Fully automated logistics hubs rapidly load customized freight pods, ready to shoot critical tech components across the globe in a matter of hours. Managing a $900 billion megaproject requires unprecedented logistical and financial oversight. Control centers run continuously, tracking every ton of titanium and every hour of labor, constantly adjusting to prevent massive cost overruns. The immense electromagnetic forces required to levitate the pods could disrupt human biology and electronics. Factories continuously press specialized mu-metal shielding to wrap the pods, protecting passengers from the intense magnetic fields. Breaking the sound barrier inside a sealed metal tube creates deafening sonic vibrations. Automated lines apply thick acoustic damping foam to the framework, designed to absorb the shockwaves and prevent catastrophic structural resonance. Safety requires understanding failure. In extreme testing bunkers, engineers deliberately crush scale models to study the catastrophic effects of a vacuum implosion. Understanding this terrifying dark side is essential to preventing it. To mitigate environmental impact, autonomous underwater vehicles patrol the route constantly. These drones use advanced lasers and cameras to monitor marine life, ensuring the immense magnetic fields and physical structure don't disrupt delicate deep-sea ecosystems. The journey must end safely. At the terminal stations, massive underground airlocks are constructed. These gigantic steel gates allow pods to transition from the vacuum tube back into normal atmospheric pressure without losing the vacuum. Before entering service, every pod undergoes a rigorous final inspection. Automated polishing arms and ultrasonic scanners ensure the sleek carbon fiber hulls are absolutely flawless and ready to withstand the extreme stresses of near-supersonic flight. Inside the sleek, highly efficient departure terminals, the boarding process is seamless. Passengers load into the pods through precision-aligned airlocks, completely isolated from the massive industrial vacuum machinery operating just beyond the walls. In the Launch Control Center, operators initiate the sequence. The massive airlocks seal perfectly, the final atmospheric pressure is vented, and the electromagnetic coils power up. The pod is ready to be fired across the ocean. The verdict? Building a vacuum tube across 3,000 miles of erratic ocean floor is currently beyond our engineering limits. Maintaining a vacuum against crushing pressure is arguably harder and more dangerous than colonizing the moon. However, crazy ideas push us forward. Even if we never cross the Atlantic in a tube, the materials and magnetic tech developed for this dream will revolutionize short-distance travel, giving us floating bridges and faster cities. So, the question remains, if we built it, would you be brave enough to step into a glass vacuum tube and fire yourself through the abyss? Let us know in the comments below, and don't forget to subscribe.